Welcome to part one of our video series on estimation. In this video, we are going to cover the following topics. First, we're going to discuss what is a parameter. Then we are going to discuss the classical method of estimation, and finally introduce the idea of interval estimation. I'm Renee Clark from the Swanson School of Engineering at Pitt. Okay, so first, what is a parameter? Okay. A parameter is a number that characterizes a population. Okay, so mu, or the population mean, is a parameter, or sigma squared is a parameter. That is the population variance, or sigma itself, the population standard deviation, is a parameter. Okay, now that's as opposed to a statistic, also known as a descriptive statistic, which is a number that's computed or describes a sample of data out of a population. So for example, X bar, or the sample average, is a statistic, or S squared, or the sample variance, is a statistic. Okay? Now, while statistics are known, they're known values, a parameter is typically unknown, okay? So we must estimate it, typically, using inference, or the process of statistical inference. Okay, so estimation is a form of statistical inference. Okay, and in this course, and going forward in this video series, we are going to discuss the estimation of multiple parameters. Okay, so for example, we're going to discuss how to estimate the population mean, okay, mu, from a single population, as well as the difference between two means, mu1 minus mu2, from two populations. We're also going to discuss how to estimate the proportion from a single population, which we denote as P, as well as the difference between two proportions from two populations, P1 minus P2. We'll discuss how to estimate the variance from a single population, as well as the ratio of two variances from two populations. Okay, and in doing this estimation, we'll be applying the sampling distribution theory, or elements from the sampling distribution theory that we have been discussing in the prior videos, including the central limit theorem, which will play a key role. Okay, so this course will definitely does build upon itself. Okay, so let's first discuss what's known as the classical method of estimation. Okay, in the classical method, a statistic is calculated based on or from a sample, which is taken from the population, just as the picture on the right shows. Right, here is a sample taken from the population. Okay, we calculate the statistic X bar. X bar is a statistic. Okay, now a statistic such as X bar is also known as a point estimate. Okay, and a point estimate is just simply a single value that's calculated from a sample. Okay, and it's a number that sensibly estimates the population parameter. So for example, X bar is considered a point estimate for mu. Okay, X bar, or the sample average, sensibly estimates the population average, right? And this would be as opposed to S. The sample standard deviation would not be a sensible estimator for mu, right? You wouldn't use the sample standard deviation to estimate the population mean. You'd use X bar instead. Okay, now with a point estimate, you're going to expect some error between it and the true parameter value, okay, because that point estimate, okay, is based on only one sample, and you can take many different samples out of the population, okay? So those point estimates or those statistics, as we learned, vary sample to sample. So they're random variables. So you're always going to expect some error between the true value and a point estimate based on just one sample out of the population. Okay. Thus, a point estimate, such as x bar, is unlikely to equal the parameter value, mu in this case, exactly. Okay. For this reason, it's actually preferable to calculate what's known as an interval estimate for a parameter. So for example, we may be able to calculate with a certain degree of probability or certainty or confidence that the parameter value mu is, for example, between 12.1 and 12.9. Okay? An interval estimate tends to be more informative than a point estimate. Okay? This whole slide actually serves as the basis for the very important topic in inferential statistics known as confidence intervals, which you will be hearing a lot about as we go forward. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.